So a quick recapitulation. The mechanics, the subject which deals with the behavior of any object when it is subjected to some force. The different objects, its properties, it may be solid, deformable solid, non-deformable or perfectly rigid solid. Then it may be liquid, it may be gas. So depending on the object, etc., it is that type of mechanics. So whether it is engineering mechanics or mechanics of deformable solids or liquid mechanics and gas mechanics combined in the subject fluid mechanics, whatever it may be. Then different kinds of forces. It may be constant, it may be time varying, it may be a function of other parameters. So many such things. And mainly we divide this subject in two broad categories. One is the static analysis, other is the dynamic. The dynamics part is comparatively very new because that measurement of time is very much required there. Okay, now to start with, for the static, suppose at a particular point two forces F1 and F2 are acting, how to understand what is the magnitude of the resultant is not simple addition of these two quantities that you know. So this is the law of parallelogram. Then from that we shifted to this non-concurrent forces as such on a plane. When two locations B and C are there, two forces F1 and F2. Now we can easily draw this parallelogram with the magnitude and direction of F1 and F2, but the exact position or the line of action of the resultant, we need to find out the point of intersection of these two lines of action extended, force F1 and force F2. So then resultant of that much determined magnitude and direction with suitable scaled value, and it is passing through this. Now you just think about this parallel forces. Now when we have two parallel forces, suppose at B one force F1 is acting, is fine. But C, the force F2, it is not inclined to F1, it is parallel to F1. Then in that case, what about the magnitude of the resultant?
F1 plus F2.
F1 plus F2, fine. But geometrically, how we can understand that it is F1 plus F2?
Sir, we have to move the initial point of any one of the vector to the end point of the another vector.
So move the tail of the F1 to the head of the F2.
From the first point of the first vector F1, we get this force F1. This is the terminal point with that arrowhead. Then from this point, we draw a line which is the free vector of F2. So from this point, we draw F2, which is parallel to F1 again. So it is simple straight line extended, and F1 plus F2 becomes the resultant. Now the important thing, what is the point of application of that resultant force F1 plus F2? F1 is here at B, F2 is here at C parallel to F1. Then what about the point of intersection of these two parallel forces? There can't be such thing. So how to find out? Of course, it is the primary mathematics or the oldest mathematics, that the geometry. So how to find out geometrically the position of the resultant? Of course, from our common sense, we can say if F1 and F2 are of same value, then it will be at the middle between F1 and F2. But if those are of different values, then we can say, sir, there is a formula. F1 multiplied by A, F2 multiplied by B. That is from so many things are there. But one primary thing that we have discussed earlier, now we can utilize that part. These are some extension of that. Instead of this parallelogram, it's a triangle. Triangle may be F1 plus F2, or that commutation F2 plus F1, etc. For more number of forces, gradual vector addition, etc. Now, this is resolution of forces. We discussed it in our previous class. That. Can you see this diagram?
Yes, sir.
Yes, sir.
So this force R or this vector R is given, and then you arbitrarily select different points in that plane. Here is a point, complete this triangle. Here is a point, complete this triangle with using that point as the vertex opposite to this given vector. Then here is the third point. Now when you complete this triangle or form this triangle, we can say that this is summation of two vectors like these green lines f1 and f2. So f1 vector and f2 vector, when those are added, we get this. Similarly, from this triangle, these two red lines and this blue line, it is a vector summation of the forces f3 and f4 will give us this thing. This is the simply the reverse way. Similarly, f5 plus f6. So this opposite process is applicable for unlimited number of such combinations. Okay, now that combination we can make according to our convenience. So here is that our convenience. We consider this point where we complete this triangle, this point as the opposite vertex to this vector f in this triangle. Then these two lines are perpendicular to each other, and we can frame it on this Cartesian coordinate systems x and y mutually perpendicular to each other. In that case, this part is called the x component of the vector f, and this is the y component of the vector f. It is simply this kind of resolution. Okay, now this thing we utilize for this situation. So at B there is a force F1, at C there is a force F2 not inclined parallel to F1. Now we resolve this force F1 in two components. Maybe those are F3 plus F4, and resolve this force F2 which is parallel to F1 in two components F5 plus F6. So ultimately what is the F1 plus F2? It is F3 plus F4 plus F5 plus F6. So I'm not going to write all these things in detail. It's very easy to understand and visualize. Now this system of two vectors F1 and F2 parallel to each other is equivalent to 4 vector summation, that is F3 plus F4 plus F5 plus F6. Now if we can consider any two of these components out of these 4, for F3 and F4 corresponding to F1 and F5 and F6 corresponding to F2 parallel to F1. If we consider, we select two those vector components, one from this F1, other from this F2, whose magnitudes are same, directions are opposite. Suppose F4 and F5, those are equivalent opposite. Then what about the vector summation? F3 plus F4, then F5 is minus F4.
0.
Not 0.
F3 plus F6.
Sir, please repeat the question again, sir. आवाज नहीं आ रहा।
आवाज आएगा बेटा, मैं कुछ लिख रहा हूँ, तो पढ़ने का कोशिश कर। So now, do you get my point? Resolve F1 in these two components, F3 and F4. Now this F3 and F4, they cannot be parallel to each other or parallel to the given force F1, any two direction. Then resolve F2 in F5 and F6. Done. Then you make this F4 and F5 equal and opposite to each other, then what happens to this equation?
F3 plus F6.
F3 plus F6.
F3 plus F6.
So F4 and F5 are equal and opposite to each other. Done. Then the resultant R is F1 plus F2, that is equal to F3 plus F6. Okay. Now what do we get from this? Resolving the forces F1 and F2. We get these two forces, the resultant force R corresponding to the two parallel forces F1 and F2 is F3 plus X6. Now are these forces F3 and F6 parallel to each other? Because drawing those lines in our hand, and we intentionally make this resolution in such a way that in any sense F3 and F6 cannot be parallel to each other, and definitely there will be some point of intersection. And geometrically we find that points of intersection by extending the lines of action of the forces F3 and F6. And through that point the resultant F1 plus F2 is acting. It's very simple, and you can try it with your paper, scale, pencil, eraser. That's all. Okay.
Yes, sir. Yes, sir.
So geometrically it is very interesting, and you will find rather you will enjoy to play with these geometries. Then we discussed about these details of summation of mode number of forces, etc. Then this is the way how we resolve it. According to our convenience, we select any point in that plane and draw this triangle. Now, whenever we have drawn any triangle, suppose this first one, F1, F2, and R. Now, these lines have their lengths equal to the magnitude of these forces, rather geometrically it is represented. So there must be some suitable scale. Suppose 1 centimeter represents 100 Newton, etc. So if it is 5.5 centimeter, if it is 7 centimeter, and somehow it is 8 centimeter, so it is 800. This is 550, and this is 700 Newton. In that way. But from your school syllabus, the property of this triangle, can you remember that sine law?
So
length of this line divided
sine
by
A by A is equal to sine B by B equal to sine C by C.
so this magnitude of F1 divided by sine of this angle, included
Yes,
angle, that is equal to magnitude of F2 divided by sine of this opposite angle.
Opposite angle.
That is equal
Yes,
to R divided by this angle, sine of this angle.
yes, sir.
Now, very important.
So that is Lami's theorem.
That is not Lami's theorem. Lami's theorem is represented in some other form using the sine laws, where those angles are not included angle between the forces or these three sides, capital A, capital B, and capital C.
Yes, sir. It is sine rule. This one is.
This is sine
It is
rule.
sine, but we can.
It was present in the properties of triangles.
Okay. Now, one thing we can do. Can you remember that we can shift the position of the point of application of the force along that line of the force, line of action of the force, without changing the effect of that force. So if we have three forces F1, F2, and R, suppose it is in equilibrium. So R is not that resultant of F1 and F2. So in that case, R should be opposite to this direction. So F1 plus F2 plus this, as it is shown, it should be minus R. So F1 plus F2 minus R, that is equal to 0. That is the equilibrium. Any name you can give. Now, if you consider this force system, or maybe this concurrent force system here directly. Now, if three forces are there, one is F1, other is F2, not according to those green line directions. Suppose F1, F2, and F3, these three forces are acting, and they are giving a closed vector polygon, that is a force triangle. Now, from that force triangle, you can draw this F1 plus F2 plus F3, that is equal to 0. And there you utilize the sine law. Now, one thing, remembering that the point of application of the force can be shifted to any location along their line of action. So if it is F1, we can shift this point of application B to some other location. We can shift this point C to another location. Suppose these are overlapping, and we can consider that minus R force, that is the equilibrium force or the third force. It may be F3, whatever it may be. F1 plus F2 plus F3 is equal to 0, giving us that equilibrium situation. So in that case, we can draw three lines, one along F1, other along F2, and the third one along the equilibrium or F3 or minus R, whatever you like to call it. Then for that particular point, we have drawn three lines. Triangle is different issue. It is the three vector lines connected one after other to get a triangle. But in this case, when that concurrent force situation is given at a particular point, three forces F1, F2, and F3 are given, then the included angles between F1 and F2, included angle between F2 and F3, and included angle between F3 and F1, those external angles are not same like this. So instead of, suppose we consider a particular point here, anything, then draw F1 through that point in this direction, parallel to this green line F1, then F2 parallel to that here, and F3 it is vertical upward. Then the angle between F3 and F1, angle between F1 and F2, and angle between F3 and F2, those are not these things. Those are 180 minus this angle, 180 minus this angle, and 180 minus this angle. Of course, sine 180 minus theta, that is sine theta. So this A divided by sine A, B divided by sine B, as in its familiar way you can remember. So small a divided by sine capital A, that is equal to small b divided by sine capital B.